Alright, so this is a presentation on P5 waves. I'm just going to read through these slides, just me reading through these slides. I'm just going to read through these slides. I don't know why I'm repeating that 3 times, but let's go. Actually, let's just do this first. So the objectives on the left-hand side. Describe wave motion in terms of amplitude, wavelength, frequency, and period. What is the amplitude? The amplitude is the distance between the equilibrium position. Now, the equilibrium position is this dotted line here. So if you look at my cursor, look at this cursor here, and then follow the cursor, and this is the dotted line is the equilibrium position, and then the crest is at the top, the trough is at the bottom. So the distance between the equilibrium position to the crest is the amplitude, and the distance between the equilibrium position to the trough is also the amplitude, assuming it is assuming it is the same height, assuming it doesn't lose energy, assuming it's a perfect wave. So that's the amplitude. Amplitude is the distance between the equilibrium position to the crest or trough. What is wavelength? Wavelength is the distance from one crest to the next crest. So this crest is here, and the next crest is there. So it's the distance from there to there. And the amplitude and wavelength have the same units. So because it's a unit of length, it would be meters. Frequency. Frequency is the number of waves, oscillations, revolutions, cycles per second. So if we read here at the bottom, frequency, the number of crests or trough that pass through a given point in a unit of time. That's also true. The number of crests or troughs that pass through a given point per time. Unit of time is second. And the equation is frequency is equal to 1 over the period, or F is equal to 1 over T, and it's measured in hertz. So frequency is measured in hertz. And what's the definition of period? What is period? Period is the time it takes for one complete oscillation, or one complete cycle, or one complete revolution. So it takes the time it takes for one complete revolution. That's the period. Okay, so we then define wavelength and frequency. Describe and apply the relationship between wavelength, frequency, and wave velocity. That is over here. So let's have a look at the example. What is the wave speed when the frequency is 20 Hz with a wavelength of 3 meters? Use the formula V equals F lambda. So F in this case is 20 Hz, lambda is 3 meters. You times them together, you get 60, and then you put meters per second there. So you times those two quantities. The question, what is the wave speed when the frequency is 25 Hz with a wavelength of 4 meters? You times them together, because V equals F lambda, F is 25, lambda is 4 meters. You times them together, you get 100, and then the units will be meters per second, or yes, meters per second, so it's 100 meters per second. The next one, so we still have applied the formula. You need to, when you read a question, make sure you locate the frequency, locate the wavelength, just find the two quantities together, and then you rearrange the formula and then solve. Okay, describe differences between transverse and longitudinal waves. So it is over here. Longitudinal is on the left, transverse is the right. Longitudinal wave is when the particle movement is moving parallel to the energy transfer. In this case, the energy transfer from left to right. And as it's linky, because it's a slinky, the particles will move parallel. So in this case, the wave is going from left to right, and also it's going from left to right. So it's going left to right like so, like my mouse is doing, like what my cursor is doing, left to right. Okay, so that's longitudinal waves. The vibrations are parallel to the direction of energy transfer or wave travel. And if you look at transverse wave, it's going up and down, while also moving left to right. So the vibrations are moving perpendicular to the direction of energy transfer. So if the energy transfer is moving from left to right, the vibrations are moving up and down. We haven't reached the end. If you look at this last one here, the last objective, show how changes in velocity, frequency, and wavelength in transmission of sound waves from one medium to another are interrelated. Okay, so let's have a look at this one here, how sound travels. If it's a solid, because, have a look at my mouse over here, sound travels fastest through solid because the molecules are packed tightly together. Sound can't travel through empty space where there are no molecules to vibrate. So, because in a solid, the atoms are closely packed together, the energy transfer will be easier because the sound won't be able to travel through a gas, because assume there's empty space. Is it really empty? Oh yeah. Well, compared to a solid, it will be more empty compared to a solid, because in a solid the atoms are really close together. In a gas, the atoms are far away. So sound can't travel through empty space where there are no molecules to vibrate. In a solid, the sound will travel faster. Now, if you look at this grey box here, so the speed of sound is not always the same. Remember that sound is a vibration of kinetic energy passed from molecule to molecule. The closer the molecules are to each other and the tighter their bonds, the less time it takes for them to pass the sound to each other, and the faster sound can travel. It is easier for sound waves to go through solids than through liquids because the molecules are closer together and more tightly bonded in solids. Similarly, it is harder for sound to pass through gases than through liquids because the gaseous molecules are further apart. The speed of sound is faster in solid materials and slower in liquids or gases. The velocity of a sound wave is affected by two properties of matter, the elastic properties and density. Now, you only need to know the grey part. The yellow part, you can just pause and read it. I don't need to. Let's look at this one here. Now, because warmer air, it is more random compared to cooler air, because cooler air, the movement is less random because it has less kinetic energy. Warmer air has more kinetic energy. So because it has more kinetic energy, it is less dense, it will rise, and it is more random. So why does sound travel faster in warm air? Well, because the kinetic energy is easily transferred. However, why does it say sound travels further at night when it is cooler? So just because it travels faster doesn't mean it travels further. I mean, you can think about it as, what can you think? I mean, on average, something can travel faster, but it doesn't necessarily mean that it will travel further. It could just mean that at that split moment it travels faster. But then over time, it's something to do with the collisions, because there are more collisions in warmer air. So although the speed is faster, it could be moving in a zigzag fashion. So when it says that sound travels further, it means that it travels further from its point of origin. Now that's because when it's cooler, it is less dense. It is actually more dense, not less dense, but more dense. So cooler air is more dense because it sinks. And also because sound is longitudinal, just put all those ideas together. You should be able to work out why sound travels further at night. Number one, cooler air is less random. Warmer air is more random, so sound will go in all directions. Warmer air means that sound will go in all directions. For cooler air, because it is more dense and because sound is longitudinal, it is more likely to be more focused, the sound waves, and so therefore it travels further at night. I've given you the ideas. You should be able to explain why sound travels further at night. Let's have a look at this one here. I'm just going to read this. So the diagram on the left shows deep water and shallow water. The wave direction is going from left to right. Okay, and then the refracted wave direction, the wavelength gets shorter and the speed gets slower. So let me just read this very quickly. The speed of a wave is dependent upon the properties of the medium through which the waves travel. So if the medium and its properties is changed, the speed of the waves is also changed. The most significant property of water that would affect the speed of waves traveling on its surface is the depth of the water. Water waves travel fastest when the medium is the deepest. So if water waves are passing from deep water into shallow water, they will slow down. This decrease in speed will also be accompanied by a decrease in wavelength, and that's because using v equals f lambda, if lambda goes down and f stays the same, v goes down. This decrease in speed will also be accompanied by a decrease in wavelength, so as water waves are transmitted from deep water into shallow water, the speed decreases. Just remember the last sentence. The speed decreases, the wavelength decreases, and the direction changes. So we got the wave definitions there. Those aren't the exact wave definitions. I'll probably give you the wave definitions later on. They're a bit more technical. This is a bit less technical. Alright. Did I read this? You can pause it and read it for yourself. This is just to do with the refraction of sound.